We're going to go back to permutations. Now we're going to look at a fourth case. Everything we looked at before was arranging things just in a nice, neat, straight line. But what if we were going to arrange objects in a circle instead of a line? How does that change things? So what is the difference? Well, it all really comes down to just how you can place the first object. See, when you've got a line, say there's our line, the first object, well, I've got a starting point, I've got a finishing point, which then defines every one of these positions. And so in this case, I've got 6 different spots I could put the first object. But when I have a circle, there is no start or finishing position. So there actually is only one spot I can put the first object. And then that is in the circle. Because you can rotate the circle. So say I put it in the top one and go, oh, fair enough. But if I put it in the bottom one, I could rotate the circle and it becomes the top one again. So it doesn't matter where I put it, it's always in the same position because I can just turn the circle. So the first object has one position, but then once you place that first object, now you can define the positions because you can say, oh, well, there's one to the left of that object or 2 to the right of that object and so on. But it's not until there's an object in the circle you can define the positions of the circle. So we don't have a start or finishing point. So how does that change things? Our line, we know the first object, end positions. Whereas circle, 1 position. Now it comes to the second object. The line, n-1, but now the circle, it's also n-1, because the spots are now defined. So everything stays the same now, n-2, and so on, until we get to the last object. So the difference is simply, what we're really doing is divided by the number of ways we could arrange that first object, n. So we end up with n-1 factorial. So n factorial if we're arranging a line, n-1 factorial if it's in a circle. Okay, so a meeting room, often we meet round tables, 10 chairs, committee of 10 people, including 3 teenagers. Yes, we're letting 3 of them on this committee. How many arrangements are there in which all 3 sit together? Because, you know, they're very intimidated. Going in there with 7 adults. Oh no, we want to be together. Look after the condition first. The 3 teenagers wish to be together, so in their little group, there's 3 factorials. I haven't put them in the circle yet, so it's still 3 factorial. Now we're going to arrange the objects. We have 3 teenagers, another 7 people, so 8 objects altogether, but we're arranging it in a circle rather than a line, so it's 7 factorial, not 8 factorial. And we get our answer. So 30,240 ways of doing that. So now we're going to hold an election. We're going to elect the chairperson and the secretary. What's the chance? Now there's a probability question. What's the probability that they're directly opposite each other? Well, if there's no restrictions, then 10 people, but in a circle, 9 factorial. Now, with restrictions. So, okay, we're going to elect the president and go sit down. So we've got our winner. Congratulations, Mr. President. We changed your title. I know you thought you were going to be called chairperson, but now you're president. I changed the name anyway. There's only one spot. They go and sit in the circle. So now the secretary, how many spots have they got? Yeah, got to sit opposite them. Then the other 8 people are going to sit down. How many ways of arranging those 8 people? 8 factorial. So we get 1 times 8 factorial over 9 factorial. 1 in 9 chance. Mind you, if you think about it, president sits down, there's 9 seats. Only 1 seat's opposite the president, therefore there's a 1 in 9 chance that the secretary's sitting opposite the president. Sometimes logic can solve these problems very quickly. Let's look at an HSC one. 7 people, round the table again. How many are possible? 7 people, round the table. Now it's 6 because there's no one in the circle. So we're arranging them in the circle. 6 factorial. Okay. 2 people, Kevin and Jill, refuse to sit next to each other. So how many arrangements are possible? So they do not want to sit next to each other. Well, it's usually a lot easier to work out how many ways that they do sit next to each other and then subtract that from the total number of possibilities. So I'm going to do that. Okay, Kevin and Jill together, 2 factorial ways. They now become one object. So we're arranging Kevin and Jill and another 5 people, 6 objects all up, in a circle, 5 factorial. Because we haven't placed anyone in the circle yet, so 5 factorial. 240. Oh, but of course that's not our answer. Subtract from total number of arrangements, because that will tell us how many ways we're there not together. 480. Here's just a little, I guess, flow chart, if you like, sort of how we approach these questions. So all of our permutations and combinations, you may have noticed that it's without replacement. As soon as we can reuse an object, the only option we've got is to go to the basic counting idea and use that. So all permutations and combination hints that we don't replace the object. So without restrictions, well then we have a look at it and go, okay, we've got combinations, that's where the order is not important, or we might have a permutation. But if we have a permutation, now we have a situation where we say, oh, are we in a line or are we in a circle? So we've got to make that decision. And then if we are in a line, are we using all the items or are we using some of the items? And then, of course, are some of them the same or are all of them different? So they're all the different thought process I guess we've got to go through to solve our problems. Very old HSC question, but this one's good because it sort of shows how the same question can be asked a different way and get different results. So we've got like a keypad, A, B, C, D, E, F, G, H, and there's a 3-letter code. So how many different codes are possible if the letters can be repeated? So I guess it's like a pin number. We're just going to hit 3 buttons, bing, bing, bing. Well, in this case, it's a basic counting principle because I can use the same letter over and over again. So basic counting principle, 8 times 8 times 8, 512. And the second one, they changed the rules. The order is important. We've got to actually physically go 1, 2, 3, but not hit the same button. So that's a permutation. So 8P3, there's 36 different codes. The third one was the one I was thinking down, where we hold the 3 buttons down at once. So the order's not important because we're just hitting all 3 at once. So now it becomes a combination. 8C3, 56. So 10I